Hello and welcome back to the next review video for the Algebra 2 Regents exam coming up soon. Today's video is going to focus on quadratic functions and their algebra. And we're going to break this into two videos because this is a fairly sizable unit and we want to make sure we spend enough time on each topic. So here's what to expect in both videos. In the first video we're going to start off by looking at the lesson overview, the Common Core standards, and then we're going to get into some topical reviews with the basics of quadratic functions, including factoring and the zero product law. And in the second video, we're going to start by looking at more complex quadratic situations, such as quadratic inequalities, completing the square, and then we're going to get into equations of circles, even though they're not parabolas. This is the best place to fit it in the whole year because it's its own little standard. And finishing off with the summary of the most important things that you need to know from this unit. Here are the lessons that we have learned in this unit. We had 11 lessons. So just to get a sense of what this unit looked like and how it's structured. And we have some slides to show you that have the Common Core standards that are associated with this unit. So pause the video now, just get a sense for these standards. Okay, here's some more Common Core standards, so pause the video now and get a sense for these standards. Notice this is the only geometry standard that they have here in Algebra 2, and it's in this unit. And here's a final slide of Common Core standards, so just pause the video now and get a sense for these standards. Now you may have noticed that a lot of these standards, especially these two, are reused in a lot of units because they're based upon different types of functions. So in this specific function we're looking at some kind of polynomial functions, which are the quadratic ones, which is the highest exponent of it squared. Okay. But these standards apply across the curriculum, so you'll see them revisited now and then. So let's get into some review. First, let's take a look at the basics of quadratic functions. A quadratic function is a function that is in the form ax squared plus bx plus c. And sometimes you'll see it with function notation like f of x is equal to ax squared plus bx plus c. And it's important to note that for both of these, a can never be 0. If you had 0, then you just have a linear function, okay, and there'd be nothing interesting about that in terms of quadratics. So let's look at the graphs and talk about some parts of the graphs. So you have two different types of quadratic functions. One is a positive parabola, one is a negative parabola. And the way you can tell if it's positive or negative is by examining your a value. If a is greater than 0, or in other words positive, it's a positive parabola. Looks like a smile, it's happy. And if a is negative, less than 0, that's going to be a negative parabola. It's sad. It's a frown. Okay. In the equation as well, the value of c is the y-intercept. So it could be positive, it could be negative, it could be 0, it doesn't really matter. It could be any number you want. That would be the y-intercept. We also have zeros on the graph, also called the x-intercepts. So these are zeros. And we also have a line of symmetry called the axis of symmetry. And that goes down the middle of the parabola, and it's always a vertical line with these quadratic functions. Okay. Axis of symmetry is going to be found from the equation using x equals negative b over 2a. And that's going to be a very helpful formula to know because that will help us find the vertex of a parabola. There's also other ways, such as completing a square, which we'll see in the second video. But that's probably the easiest way to find the vertex. Just use negative b over 2a. That gives you the x-coordinate of the vertex, which is the very minimum point or the very maximum point. So note if I say that the quadratic function has a minimum as a vertex, then you know it's a positive parabola. And if it has a vertex at its maximum, it's a negative parabola. The domain and range of these functions depend upon where the vertex is. Okay, the domain is always going to be all real numbers. Okay, you can plug in any value you want into the x in the function and you can get an output. However, the range is going to be dependent on the vertex. Okay, so for instance, wherever the vertex is in a positive parabola, it's going to be that value and above. So you might have something, for example, y is greater than or equal to 16, or y is less than or equal to -2. Okay, it all depends on where the vertex is. So to find the range, you have to find the vertex. Okay, as always, pause the video as we go along if you need to write anything down before we go on to the next slide. I skipped a slide. Okay. Factoring. Factoring is one of those techniques that is used a lot, especially in algebra, to solve equations, to reduce fractional expressions, and so forth. There's a lot of applications of factoring. So let's review the very basic types of factoring. So I provided some examples of each just to illustrate each type of factoring. We'll start off pretty easy with the common factoring. What you do with the common factoring is you look at the numbers, then you look at the variables in each term, and you find out the highest factor they have, all terms have in common. So in this binomial, the 8 and the 12, the highest number they have in common is a 4. In terms of variables, you can take the highest variable that has the lowest exponent. So x squared is going to be the highest factor of the x cubes and the x squareds. Once you find that common factor, then in parentheses you're going to write what's remaining after dividing that common factor from each term. So if you divide 8x cubed by 4x squared, you get left with a 2x. Notice all the signs stay the same, so minus. And then divide 12x squared by 4x squared, you get just 3. There is your factored form using common factoring. Trinomial factoring, there's two different types of that, and we were going to first look at the very basic one where the first leading coefficient is a 1. Okay, that's the easiest type of trinomial factoring. And what you want to always do is you want to find two numbers that multiply to the constant term that add to the x term, the coefficient of the x term. And there's several possibilities for 20. You have 1 and 20, 2 and 10, 4 and 5, but the two numbers that multiply to positive 20 and adds to negative 9 are going to be negative 5 and negative 4. And there's your factored form. Sometimes it takes a little bit to figure out what they are, but essentially it's going to be the two numbers that multiply to the constant term and add to the coefficient of the x term. A difference of perfect squares, so notice specifically difference, doesn't work for sums of perfect squares. It's not a sum of perfect squares, but only difference. So if you see something like 4 plus 25x squared, okay, that is done. Can't factor. But if it's a difference of perfect squares, then you can factor it into two factors. Well, what you do is in each factor you take the square root of each term. So square root of 4 is 2, square root of 25x squared is 5x. And that's what goes in both factors. But in one factor you put a plus, and in another factor you put a minus. And I suppose if you're more optimistic, you probably put the plus first. If you're more pessimistic, you might want to put the minus first. But anyways, that's how you do difference of perfect squares. Okay, so there's another trinomial factoring method, which is where the leading coefficient of the quadratic expression is not 1. And that involves a little more thinking. Okay. What you have to do is you have to look at the factors that multiply to 6 and the factors that multiply to 10. So I'm going to deal with 6 first and then 10. Okay, so I'm just going to list them out. 6 has 1 times 6 and 2 times 3. Sometimes you can get lucky, so if the leading coefficient is 5, then you know there's only one choice. You don't have to think about it. But in this case, there's two choices that multiply to 6, so we have to think about this a little bit. For 10, we have 1 times 10 and 2 times 5. Okay. Now sometimes you end up with numbers like 36, which has a lot of factors to it, so it takes a little more time to factor those ones. But the goal is to combine a pair of numbers from the 6 and a pair of numbers from the 10 that when combined, when you multiply and add them together, you come up with that middle term of negative 17. Okay. So it's very similar to that last type of factoring, except for we're just dealing with 1 times 1. Okay. Didn't really have to think too much about it. So looking at these choices, okay, you may say, okay, 1 and 6, 1 and 10. So if I multiply the 1 and the 1 and the 6 and the 10, that gives me 61. That doesn't work. It's way too large. And likewise, 6 times 1 is 6. 10 times 1 is 10. So that's 16. That doesn't work. Okay. And if you keep looking, checking, you'll find that 6 and 1 and 5 and 2 work. Because if you take the 6 and multiply it by the negative 2, and if you take the 1 and multiply it by negative 5, that gives me negative 12 and negative 5, which makes negative 17, and that's what we want. Okay. So what that's going to tell me, since 1 and 6 are going to be my factors from the 6, is that in front of the x I have a 1x and a 6x. You don't have to write the 1x. Okay. And it doesn't matter which order they go in, just as long as the next numbers pair up. The 6 had to multiply with the negative 2, so the negative 2 has to go here. And the 1 has to multiply with the negative 5, so the negative 5 has to go here. So there is your factored form. Now with these types of factoring, it's always, I think, a good idea to double check it by multiplying it out. Okay, let's just check it. 6 times x squared is 6x squared. X times negative 5 is negative 5x. Negative 12x plus 10. Look at that. That gives you negative 17 as a middle term. Yeah, it works. Always a good idea to double check it. Now let's look at factoring by grouping. When you factor by grouping, typically you're going to have 4 terms. Okay. What you want to do is you want to group a pair of 2 together and find the common factor of 2 of them, the pair together. Okay. So if I look at the 4x cubed and the 8x squared, find just a common factor in there. I notice they have a common factor of a 4x squared. And when I take a 4x squared out of just those 2 terms, I'm left with an x plus 2. Now with the grouping method, you want to have the same result after a common factoring as you did in the first pair. Okay? Otherwise you can't do factoring by grouping. And if I want an x plus 2, then what I got to do is I got to take out a negative 25. Because a negative 25 times x is x, negative 25x, and negative 25 times 2 is a negative 50. Okay, so that works. So be careful about these negatives. Sometimes you have to be, so if I just took out a 25, then I'd have a negative x minus 2, and you want to have these be the same. Okay. Now that I've grouped 2 by 2, and I have factored out a 4x squared and a negative 25 and have results of x plus 2, I can kind of do common factoring again because we now have essentially 2 terms. Each term has an x plus 2 in it. So I'm going to factor out an x plus 2 and write down what's remaining. So in the first term, I'm left with a 4x squared, and in the second term, I'm left with a minus 25. Okay, and from there, we're going to get to the next slide about complete factoring, but no, I'm noticing that this 4x squared minus 25 can factor again. It's a difference of perfect squares. The 4x squared is a perfect square, 25 is a perfect square, so might as well go ahead and finish factoring this off. Okay, so the 4x squared minus 25 breaks up into 2x plus 5 and 2x minus 5. There's your factored form. Let's look on to some last bits of factoring. Or not. Oh, have a little troubles on the iPad today, sorry. So there's a couple more factoring, and your teacher may not have shown you this, but this is, I think, a very important factoring technique to know because it relates in a little bit to the difference of perfect squares. However, with perfect cubes, you can have a sum or you can have a difference of perfect cubes that will factor. Okay. So just a reminder, the perfect cubes for the numbers are 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed, 125. Let me rewrite that. 6 cubed, so forth. Okay, those are the most common ones. So if you see those numbers plus a variable that has a power of a multiple of 3, then you know it's perfect cubed. So I see 27y cubed and 8. And the general formula for these, if you have, I'm going to write both together. A cubed plus or minus b cubed. So the plus in the top sign is going to be the, in our factored form, is going to be all the top signs. And if we have a minus difference, there's going to be all the bottom signs. So you always take the cubed root of both and keep the signs for the first factor, for the binomial factor. And then you're going to have a trinomial factor, where you're essentially going to be looking at the binomial factors that you got, these two values right here. You're going to square it, change the sign, change the sign so it's minus plus, multiply them together, so AB, and always plus B squared. Notice there's no 2's in here, like if you're doing squaring a binomial, but it's just that. Okay, that's the formula for a sum and difference of perfect cubes. So for this first example, okay, sometimes it's helpful to rewrite it like this: 3y cubed plus 2 cubed. Write it as essentially a sum of perfect cubes as one thing cubed plus or minus another thing cubed, because that's going to tell you directly what's going to go inside the first factor. What's left over is going to be the trinomial, so square the first, which is 9y squared, change the sign to a minus, multiply them to give you 6y, and then add a 4. Square the last. Now what's nice about these sum and difference of perfect cubes is that this trinomial is not factorable, so you don't have to really check for factors. There are some cases where you're dealing with maybe to the 6th power or perfect sixths that it might be factorable, but in perfect cubes, just perfect cubes, it's not going to be factorable anymore. Now let's look at a difference of perfect cubes. Again, you want to take the cubed root of the different parts, so it might be helpful to rewrite it as 2 perfect cubes being subtracted, so it's really x cubed minus 5 cubed. So we start off with x minus 5, and in the trinomial we square the first, gives us x squared, change the sign to a plus, multiply to give you 5x, and then square it to give you plus 25. There's your factored form. Now when it comes to complete factoring, okay, what you always want to check for first, is there a greatest common factor? Always factor that out first. Okay, if there isn't, then you just go ahead and use one of the techniques. And you factor until you can't factor anymore. That's what completely factoring means. Okay. Factoring until you can't factor anymore. So looking at this first example, I'm noticing that there's a 1 in front of here, and there's no x term in the last term, so I know there's no common factor in this first one. So I'm just going to go ahead and check it out. Okay. I'm noticing that it kind of looks like a quadratic, a trinomial quadratic trinomial. Because even though it's not squared in x, it is kind of, this exponent is double this exponent. So it is essentially a trinomial problem with a leading coefficient of 1. But instead of an x and an x, the square root of x to the 6 is x cubed. So I'm going to write x cubed and x cubed. Now, the two numbers that multiply to negative 64, they add to negative 63, negative 64, and positive 1. Then I have to ask myself, can those factors factor anymore? Well, I'm noticing x cubed, the 64, the x cubed, and the 1, they're all perfect cubes, so I have a difference of perfect cubes and a sum of perfect cubes. Okay, so this first factor, x cubed minus 64, will factor into x minus 4, x squared plus 4x plus 16, and this last factor will factor into x plus 1, x squared minus x plus 1. Okay, then I want to keep asking myself, can I factor this some more? Whenever you get to a linear factor, you know you're done with that factor. But these quadratic factors, notice there's no two numbers that multiply to 16 that add to 4, so that is done. There's also no two numbers that multiply to positive 1 that add to negative 1. So this is my completely factored form. I'm done with that problem. Now for the other one, I notice that there is a common factor of at least a 4 in every term. The 4 goes into 4, 24, and 32. So I'm going to factor out the 4. I'm going to use the common factoring first. I'm left with x squared minus 6x plus 8. Okay. Now I want to check that trinomial. Can that trinomial factor? And there are two numbers that multiply to 8 and add to negative 6. And those numbers are negative 4 and negative 2. Okay. And I'm noticing I have all linear factors. So therefore, I am done. Okay. So there's some review on factoring. Now let's look at the zero product law, and this is really useful when you're solving quadratic equations, because what this law is saying is that if you have a bunch of things being multiplied together and they're all equal to 0, well, the only way you're going to get 0 is if one of those at least is 0. So the zero product law says if you rewrite an expression as a product, which is essentially what factoring is, then you can solve for variables by setting each factor equal to 0. Because A equals 0, or B equals 0, or C equals 0 to make that true. Now notice it doesn't matter if A is 0, it doesn't matter what B and C are going to be. So when you plug x into those factors, it doesn't matter anymore. Because once you just have one 0, it's going to be 0. So for the zero product law, it's useful to solving these quadratic equations because we can use factoring to rewrite a polynomial as a product of polynomials. Okay? But first we need to make sure it's equal to 0. So when you see an equation like this, you want to most likely keep the highest exponent term positive. Okay, that's what you want to do. So what I'm going to do is I'm going to bring the 16x and the 24 over to the left side. I'm going to do that by subtracting from both sides. So 4x cubed plus 6x squared stays exactly what they are because there's no like terms to combine. I'm going to subtract the 16x, subtract the 24, make it equal to 0. Because what I did is I just subtracted 16x from both sides. I couldn't combine it with anything, subtracted 24 from both sides. Okay. Now I'm noticing I have 4 terms here, so what I'm going to check first is grouping. Okay. I'm going to group these first terms together and the second pair of terms together. And for these first terms, 4 and 6, the highest common factor is a 2. And x cubed and x squared is an x squared. And what I'm left with is a 2x plus 3. Now remember, I want to have a 2x plus 3 in my second factoring. So I'm going to factor out a negative 8. And notice that works. That gives me a negative 16x minus 24. By the way, some of you may notice that each of the terms is even, so you could have factored out a 2 right away, but we're going to take care of that in a little bit. Okay. We have a common factor now of this line right here of 2x plus 3. So I'm going to factor out a 2x plus 3 from each term, leaving me with 2x squared from the first and a minus 8 from the second equals 0. Now don't forget to write this equals 0. Okay, it's really important that you write that in there, because if you forget that, you can get points off. Okay, because you need to keep the same equivalent equation in each step. Now I am noticing now, okay, well I could have factored out a 2. So in this term right here, the 2x squared minus 8, I'm going to factor out a 2. When I factor out a 2, I'm left with x squared minus 4. Okay, now that looks something like I can factor some more. Because before, with the 2x squared and the negative 8, with the 2 and the 8, it wasn't a difference of perfect squares. But factoring out the 2 left me with a difference of perfect squares. I can factor some more. So I'm going to go ahead and do that. Factor in 2 and x plus 2 and x minus 2. Okay. Now I completely factored that problem. So now all I have to do is just apply the zero product law. Set each factor equal to 0 and solve each equation that you get for x. Find the x value essentially that makes each factor 0. So I have 4 factors. 2 equals 0, 2x plus 3 equals 0, x plus 2 equals 0, and x minus 2 equals 0. Okay. Now, you might be so familiar with these by now that you say, oh God, obviously the answer is going to be negative 3 halves and negative 2 and positive 2. But if it says specifically use the zero product law, you have to show this step. You have to show that each factor equals 0. Because we have seen in the readings exam where they take points off for not showing that step. That's where you're showing the zero product law. Up above is just factoring to get down to that point. But this is the key zero product law. Now notice, of course, 2 equals 0, that's not true, so that's not going to give you anything. Okay. But here, solving this equation, you have negative 3 halves, subtract the 3, divide by 2, and this factor we get negative 2, and we get 2. So our solutions to the equation are going to be negative 3 halves, comma, plus or minus 2. Notice that is acceptable. If you had the same value, one's positive, one's negative, you can write it as plus or minus that value. That's perfectly fine. Okay, so this is the end of the first video. In the second video, we're going to focus on solving quadratic inequalities, completing the square, equations of circles, and parabolas. Okay, I hope you enjoyed this video, and I look forward to seeing you in the next. Thank you for watching.